Welcome to my favorite part of trigonometry and maybe of the whole course, which is called proving identities. You did this in grade 11, but now we have even more skills to bring to this problem. We all know the graphs of sine and cosine are not the same. They're really close, but they're not the same. If they were, they would be identical. If they were, then cos theta equals sine theta would be an identity. This is identities. Identity means exactly the same, but they're not. It is not an identity. If you didn't follow proper mathematical procedural form and you decided to prove that they were the same, and all you did was say, well, I'm going to sub in pi over 4 into cos, and I'm going to sub pi over 4 in for sine, what do you think you would find? So what's cos of pi over 4? Well, it's 1 over root 2. And what's sine of pi over 4? Well, it's also 1 over root 2. The cos wave is the blue one, so here's pi over 4. They intersect at pi over 4. The two waves intersect at pi over 4, and they intersect in other spots too. This does not mean the graphs are equal to each other just because they intersect or because you happen to find one place where they are equal. So a proof cannot be found by just subbing in a number. Cos of pi over 4 does equal sine of pi over 4, but cos theta is not equal to sine theta. It has to be equal everywhere, and it's not. An example is not equal to a proof. And the example I just gave you the other day was, I said, if I'm going to make a conjecture that everyone in your class is 17 years old, and to prove that, I point to one of you, and one of you is 17 years old. I can't say, well, that's my proof. I found somebody who is 17, so it's true. It has to be true all the time. One example is not a proof. This is only an acceptable method to use if you're trying to prove that it's not an identity. And sometimes you get questions like that. You'll get a question to say, prove that cos theta does not equal sine theta. Then you would sub in a number, not pi over 4, because that wouldn't prove your answer. You'd pick something else like pi over 2. You would get two different answers. So a counter example is okay if you're proving it's not an identity. But when you have to say that two functions are equal to each other, you can't sub in to just find an example. Here are some of the identities we learned in grade 11. These are just your reciprocal identities. Cosecant is 1 over sine, all that. This is the quotient identity. The big one's the top one, that tan is equal to sine over cos. That's your main quotient identity. And then the Pythagorean identities are here, the main one being sine squared theta plus cos squared theta equals 1. Now, some new ones we have from grade 12. First, all the addition and subtraction formulas, which you don't have to memorize. I'll give you those ones. Those are all identities, are all true. This left side here, sine of x plus y, is always going to equal this. And we proved some of these already. You also have double angle formulas. This left side, sine of 2x, is equal to 2 times sine x times cos x. These are identities that are true always, no matter what you sub in for x. It's always going to have a left side the same as the right side. And these were some of the cofunction identities from section 7.1. There's just a few of them here. But there are more because you have a big list on the go somewhere in your notes with all the identities that we have, and there's a lot of them, and you don't have to memorize them all. What you see here and here I will give to you on your test, nothing more, and they're really enough to get through everything you need. But we also have some strategies. Just having a list of a bunch of formulas isn't enough. We have a bunch of strategies here that we can use to solve identities, and we're going to go over some of these in our lesson today, but you also have a lot of them from grade 11, so use your grade 11 notes, and we'll talk about, we're going to talk about canceling today and factoring, common denominators. We're going to go through a lot of these, but you do have examples of these from grade 11. All right, let's get started. Example 1, prove the following identity, and then you can check with the graph on Desmos after. You can always do that when you're done. And you'll see this graph is exactly equal to this graph. Even though the equations, the expressions look very different from each other, they are equal. And we know they are because the way the question is set up, it says prove this identity. So the question is telling me this is an identity. This is already true. but I have to prove that it's true. So part of the reason I like doing identities is because I already know the answer. I already know what it has to look like when I'm done. I don't have to figure it out. I have to get there. Okay, one important piece of form and a lot of mathematics is communication. If you don't communicate correctly, you lose form marks. We start with the left side, rewrite the left side there. We can work on that, and then we have a right side over here. But we do not keep them together, and we do not bring things across the equal sign or cross multiply or anything like that. If you do that on a test or a quiz, I'm just going to give you 0 because you're not following correctly, and that's because of restrictions, which we don't need to get into, but you have to work your left side separate from your right side. So what are we going to work with first here? Let's start with the right side because it looks more complicated than the left side. So on the right side, I'm going to factor this numerator. So if the cos is throwing you off, think of it as something else. Think of it as 2a cubed minus a. In that case, the common factor would be an a. Except we can factor out an entire function. We can factor out a cos x. So I factor out a cos x, and I'm left with 2 cos squared x because this was cubed, now it's squared, and I took out a whole cos x here. So I factored cos x out of this bracket. Now, can you see what the next step is? The next step will be to cancel that monomial. So I'm going to cross off cos x and cos x. They match exactly, so I can cancel them out. I cannot cancel this binomial with anything. You can only cancel a binomial with a binomial, and I don't have another binomial, so I can only cancel those monomials. So now that that's canceled, I have, all that's left is 2 cos squared x minus 1, and that hopefully is ringing a little bell for you, or if you've got your page of formulas, identities handy, you see that I can simplify this a little further because it's a double angle formula. I can write that as cos 2x. That is as far as I can go. We can't simplify much further than this. Does it match the left side? Does it match this side over here? No, but it almost does. And hopefully some of you can see how it matches. So let me just remind you of one of these I just talked about. We always want to put everything in terms of sine and cosine. That makes things easier, especially when you see that my right side here, I've got that all the way down to a cos. So I don't really want a sine or a tan in my answer. I would like to get everything in one ratio if possible. So how am I going to do that? So think of all your formulas you've got. If you've got your sheet handy, go back and take a look at it. Remember that tan is equal to sine over cos. That's your quotient identity. Tan is the same as sine over cos. So if I rearrange this, I'm going to multiply. This is a 1, right? I'm going to cross multiply. That gives me tan times cos equals sine. I can isolate cos, and I get cos equals sine over tan. So if cos is sine over tan, that looks a lot like this. These two are very similar. The only difference is the angle. So all I have to do is make this x here, this angle, match the angle in the original left side, and that would just be simply to change the cos x to a cos 2x. My left side now equals my right side, and I can use a little Latin phrase, quod erat demonstratum, and that means I've demonstrated to you what you asked me to demonstrate. QED, proven. When you're done, you need a statement like that that says QED at the end. You can just write QED, or you can put left side equals right side to show that's how you conclude your proof. So maybe you were thinking, oh, I was going to do that another way. For sure, there's lots of other ways. That's why I like identities so much. There's so many different ways to do it. So let's look at just one other method here. Looking at the right side again, back to the right side up to the original question, it looked like this. So here's another strategy. Another strategy is, and let me just start you off with this. Think way back to elementary school. If you had 5 minus 8 over 3, Okay, the line above that you would have had would have been 5 over 3 minus 8 over 3. So it's a common denominator, but we're kind of doing the reverse. We're splitting the denominator. So I want to take this is a common denominator of x, but I want to kind of work backwards. I want it to look like this. I want to split it apart, and that makes it look like this. So I take my denominator of cos, I split it under both. I'm kind of working in reverse there. I'm going back a step. Instead of having it over a common denominator, I have it in two parts, two terms. All right, why did I do that? I did that because now I can do some canceling. First of all, this whole side here, that's going to be a 1. And then I've got, again, if you want to think of this as 2a cubed over a, if that makes a little more sense to you, that's really, when you cancel, there's 3 there and there's 1 there, you're really left with 2a squared. But a, of course, is cos, so I sub that back in. I'm left with 2 cos squared x minus 1. And that is, of course, this line right here. So I could just, my answer would be cos 2x. So that's another way to solve the same problem. And there's lots of ways. So I encourage you to try different ways. And when you look at the back of the book, they'll have it solved one way. Maybe it's not the way you did it. It does not mean your way is wrong. And you can ask me if you're not sure, did I do this right? Doesn't mean your way is wrong. Let's try another one. Prove the following identity. This one I took out of your textbook because students often get stuck on this one. Okay, what do we want to do here? Well, there's the left side and there's the right side. Oh, that font's a bit bigger. Remember, you have to separate them. I can't move across the equal sign, so I can't just say, well, let's add sin x to both sides. No way, don't do that. That's kicking yourself out of the race before you've even started. You can't play if you're going to do that. You have to work on them separately. So usually we start with a more complicated side and we try to simplify it so that it looks like the other side. So for sure my left side is more complicated. I would like it to look like this, and believe it or not, it will. So picture the sine wave. You know the sine wave. Now negative vertical reflection on that, that's exactly the same as this over here. I already know that because the question says it's an identity. I just have to prove it. This mess is equal to this little simplified thing here. We just have to get there. So let's look at these pieces over here. First of all, that if you look back, look at this, just this part right here, and look on your formula sheet. You have a cofunction identity that matches that. That's a cofunction identity, so locate that one. It's in the box that you have with all of your formulas in it. That one is just equal to cos. So this whole piece right here, I can replace this whole piece right here with cos. Now the cotan one is a little more difficult. And we do have a whole bunch of different identities we could look at, but the first thing I want to do with the cotan one is change it to sine and cosine. So that'll be my next line. So here's my code. This whole thing is cos now. Lovely, simplified, beautiful. Cotan of this angle, I change to cos over sine of that same angle. So whatever angle is here, I have to put it here and here. It's the same angle. I can't just change it to a theta or something to make my life easier. Okay, so the angle matches this angle. Now we're all with cos and sine. Now we want it all to be sine, but at least we've got cos and sine, and that's better than cotan. Again, we have a couple of things we could do. There's a couple of ways to attack this one. The numerator, I am going to use the compound or addition formula. Remember our compound formula is from 7.2. So I'm going to expand all of this. You're going to go back and look at your addition formula, and we're going to use the cos addition formula. We're going to expand all this out. The denominator, I could do the same thing, but there is something else also with the denominator. We could also look at our cofunction identities there for the denominator, and that was from 7.1. So if you think of the sine, imagine this pi over 2 is in here. Think of sine x, just a sine wave. And then if you were to shift it pi over 2 units, what would it be? I'm actually not going to do it that way. That is a faster way, but I'm going to go the long way. So let's use the addition formula for both. So I've taken the pi over 2 and the x, and I've filled it all out with the addition formula for cosine, and then bottom, the addition formula for sine. This is maybe a little more complicated way because there's more places for me to make mistakes, but I don't have to think too hard about it because I just pull out my formula sheet, I find that it matches something, and I stick it all in there. Now, we have an exact angle, we have a pi over 2. What is cos of pi over 2? Let me give you a little sketch here. Where is pi over 2? Pi over 2 is up here at 90 degrees. So if we had a unit circle, that dot right there on the unit circle, what's its coordinate? Its coordinate is 0, 1. Remember that cos is x and sine is y. So what is cos of pi over 2? Cos of pi over 2 is 0. So cos of pi over 2 is this 0 right here. And then this cos x is this cos x. Sine of pi over 2, there's sine of pi over 2 is 1, so there's the 1. And this sine x is this sine x. And same thing on the denominator. So anytime you have an angle that you can set, not an x, but you have an angle like pi over 2, then we can go ahead and calculate that. Now I've got 0 times cos x, that's going to be 0. 1 times sine x, that'll be minus 1. So I'm just going to simplify all of this. So these are gone because they're zeros. I'm not canceling them out, I'm turning them into 0. It's not canceled, it's just 0. I'm left with this, and take a look at the right side. Always keep your eye on the prize. Look at, this is what we want it to look like when we're done, right? This is our final. Can we get there from here? Absolutely, we can get there from here. What are we going to do? We're going to cancel these cos x's because they're monomials. One's on the top, one's on the bottom, and there we get our minus sine x, or negative sine x. QED. So we have proven that one. And it was kind of complicated because we had to sub in some stuff and go to a big formula, but it worked. There's other ways to do it, but this way worked. In the back of your textbook, you will see full solutions like I've done here. They're all typed out for you in the back of the book. However, these solutions show moving terms across the equal sign, which is wrong. Terrible mistake on the publisher's part there. You cannot move across the equal sign. So if the back of the book does it, it does not mean you can do it. Let's do another one. Example 3. Secant 2 theta. We've got a secant and a cosecant in this one. Okay, think about it for a sec. So what do we do first? The first thing we have to do is separate the left side from the right side. So this one I'm going to write it all out. There's my left side. There's my right side. Cosecant theta over another cosecant. Oh, and it's tempting. Let's cancel out these cosecants. No way. You may not do that. Why can't I cancel out those cosecants? Because the top one is a monomial. The bottom one is part of a binomial. Again, if I had 3 over 3 minus 8, I can't do this. No way. 3 over 3 minus 8 is 3 over negative 5. It's not just negative 8. So you can't cancel like that. These two pieces have to go together here. You can't cancel. If you do, you've just blown your chance of getting marks for this question because you've done a horrible mistake. So don't do that. Erase that. So what are we going to do? I'm going to do one little thing with my left side here, just because I remember that tip from earlier on that you should always use sine and cos as opposed to anything else if you can. So I'm just going to, oh, sorry, that's a 2. Whoops, I missed a 2 there. 2. So this, I'm going to rewrite this as 1 over, what is secant? Is it sine or cos? It's cos. So 1 over cos 2 theta. Okay. 1 over cos 2 theta, that's that. I'm going to leave the left side there because I've got it in terms of cos, and that's really as far as I want to go with that. I have lots of double angle formulas. I could certainly take that denominator, but then I'm going to make it more complicated, more messy, and that's not the goal of a proof. You want to keep it neat and tidy. Let's go over to the right side. What can we do with the right side? Well, again, we can get rid of all of these extra secondary ratios and go back to the primary. This one I can't separate the denominator here, right? I can't write this as, I can't break it apart in two because it's not a single denominator, it's a binomial denominator. So it's not like the last one because I've got two terms on the denominator. But what I can do is take this cosecant and write it instead as 1 over sine theta. So I'm just going to put a bracket. That's that's this piece right here. Actually, I'll change colors so I don't confuse you. Then instead of this long division operation line, I'm just actually going to write division like this, divided by. Now I'm going to go to this cosecant right here, and that is also 1 over sine. So I'm going to change that to 1 over sine theta. And I have to subtract 2 sine theta. 2 sine theta. That's already in sine, so I don't want to change that. I don't want to change that to anything else. Okay, so what I've done here is I've got everything in sine and cos on both the left side and the right side. I'm working on them separately. On the right side, I've got everything with sine. But I have some levels of fractions here, so this is something I need to work on now. My 1 over sine here, let's just leave this alone. 1 over sine theta, that's pretty tidy. I don't want to mess with that right now. But my second bracket is messy. I would like to get a common denominator for my second green bracket here. So I'm going to put this is over an invisible 1. So my common denominator would be sine theta. So my common denominator is going to be sine theta. So this one already has a sine theta. How can I write 2 sine theta with the denominator of sine theta? Again, if the sign is throwing you off, change it to something else. Change it to a b. What I'm doing, whatever I do to the bottom, I multiplied the bottom by sine theta. I have to multiply the top by sine theta. So this gives me a numerator of 2 sine squared theta, and the squared goes over the word sine, not over the angle. That when it's over the word sine, it means the whole function, not just the angle. So what have we got here? And sometimes we start doing stuff and it doesn't even help, and I'm just making it worse. Every line is getting worse. I'm not even getting closer to the answer. So let's just see. Maybe we're getting somewhere, maybe we're not. Divided by, let's see if this has helped. So I have my 1 denominator of sine theta. My numerators are now the same, so I can put them together. 1 minus 2 sine squared theta. And you've always got that formula sheet handy, and you're always having your eye out for anything that matches something on that formula sheet. And something does here. Do you see what matches something on your formula sheet? And I don't mean that this is cosecant. Look at the numerator here, 1 minus 2 sine squared theta. 1 minus 2 sine squared theta, that is something. Look at your sheet. Did you find it? What is 1 minus 2 sine squared theta? 1 minus 2 sine squared theta is cos 2 theta, which, wow, look at that over here. That's nice. If we can introduce this term here, then we're looking good. So that's going to be good. Let me change that. While I do that, I'm going to do two things at once here. I'm going to take my, I can drop this bracket, I think, off the first part here. 1 minus sine theta. I'm going to change my division now to multiplication, and I'm going to flip, invert and multiply. So I'm going to flip this because I'm changing division to multiplication. So my denominator of sine theta now comes to my numerator. And my numerator, 1 minus 2 sine squared theta, goes to the denominator. But of course, that we already talked about is the same as cos 2 theta. Oh, we're almost done. Do you see it? We're almost done. These monomials are exactly the same. They will cancel out. So all we're left with is 1 over cos 2 theta. That's it. We're done. The left side equals the right side. QED. We proved it. And we proved that the left side is equal to the right side. And we proved that they are identically equal to each other. The left side and the right side are exactly the same. These questions require a lot of practice because you have to get used to subbing in those formulas and swapping things in and out until you can get your left side to equal your right side. So it requires a lot of practice and a lot of familiarity with your identities that you already have. We're not graphing any squared functions yet, and there's a few in your homework that do have squared functions, so you don't need to do those right now. We'll do them later. You can skip those questions for now. That's it for your lesson on identities. Remember, the back of the book travels across the equal sign, but you will not. And you can always check your identity. If you can't get it to work, you can't get it to work. And you think, maybe it's a typo, maybe this isn't written out correctly. Well, type them into Desmos, type the left side on one line, then type the right side on the other line, and see if they actually are an identity. They should be the exact same graph if they are an identity, and that means there is a way to prove it. And it just takes practice. So have fun.